Okay, so today we will go with the last part of our short course. We will do some practical example with Jan today, and also I will give just a few slides. But I would like to ask you first about the first 2 days. If you have questions, if you have concerns, if you have something that you dreamed with at the night about us, so just just let me know. So let's start like that. If you have any questions. So I had several questions, good questions yesterday. So go ahead.
I have just more concern about the software and the development process, the team, the backgrounds, and the challenges of developing this software.
Yeah, okay. Today we will talk about the software, and maybe this is a good thing. So usually when you work on computer science, and you need to be somehow productive. So not just, for example, in academia to write papers and other things, but you need also to develop software maybe for other researchers to use, maybe like the vision we have here in the kingdom to move everything to commercialize, even from the research area. So you need a little bit to have several skills, not just to be good in research or writing paper and other things. So for ExaGeoStat, for example, this is, for me, it was not the first software, so I had software before during my PhD, but even though we start to develop the software, the problem when you develop a software in research compared to industry, in industry you have a customer. Okay, I need this input, I need this output. Everything is clear and that's it. When you do research, the output is not clear because your job is to do research and see how to extend things or how to develop something new. This is a big problem from the software development because if you don't have an output, your design of the software may have problem at the beginning. And this is one of the challenges. I like to say challenges, not problem, that we have in ExaGeoStat. We had a plan. This is input, output, dense. This is what we want. Then, okay, we need to extend. We need to do a new approximation method. As I said yesterday, there's a new hardware in the market, which is NVIDIA GPU hardware that support mixed precision. Let's add mixed precision. From the software design, this is a big problem. If you don't have this plan from the beginning that you will add 1, 2, 3, 4, 5, redesigning the software is very hard. And this is why after 7 years, we decided to do a software engineering for the software. So actually we changed the structure of the software, not the functionality, but just the internal design with our new version. And this took about more than 1 year, and we're still on this development stage. So the problem on the software development and research, this design thing, okay? It's not easy, but as I said, you need to have an expertise on software engineering, coding, research, and also maybe some understanding of the concepts if you are working on something like HPC related to the HPC terms, okay? It's not easy, as I said, but we are trying to do our best. And this is not just our problem. This is in general in research. This kind of re-engineering the software after several years is very important.
How many years it takes to re-engineer?
Re-engineering, we took 1 year. But actually, we used 2 software engineers to do that. 2 software engineers, not researcher, to do the re-engineering. So 1 year, we're almost there. But we still, I think, maybe we need more, another 6 months. But it's not time for all the software. It depends. So it depends upon the software and your needs to re-engineer everything. But we took the advantage because we were re-engineer and we moved the software from C to C++. So we moved the language to have more capabilities and at the same time re-engineering the software. Mm-hmm. Any question? Yeah, this is a good question. So C++ compared to C, how many of you has experience with C first? C++. So both. So let me ask you this question. What do you think the difference between C and C++?
I haven't used C, but C++, you almost always need to define every piece of memory you use, makes you pick up good habits.
Okay. Yeah, you are the last one.
So the difference between C++ and C, I think C is more basic and you need to define a lot of things. I used to program some games in C before, so so basic and it's kind of a language that will define everything in the environment to work.
Exactly. Yes.
Unlike C++, where it's more structured and more like, I think, easy to use.
Okay.
I
Nice.
think also C is a procedural.
Is?
Procedural language, not support the object-oriented programming.
Yeah. This is the structure that he means. Structured language. Any other feedback? Go ahead.
C++ tend to be faster since it's half a direct.
Yeah, it seems it's faster. But to align with what they said, that because it's an abstract compared to C. So in C, you need to do everything by yourself. Memory allocation, pointers, everything. If you don't know what you are doing, actually this impacts your software and the speed up of your software. But if the same programmer, just you give him a C++, everything abstracted and well-designed and structured, he will have better software. That's it. But at the end, both software should have the same capabilities, but in a different way. Okay? So, yeah, we moved to C++ because more structured. When you have bigger software, you need to depend on object-oriented programming. You need to define different parts of the software. And what I discussed yesterday about this separation of concerns, you can do it very easy with object-oriented programming by having different object classes, interfaces, and other things. This is why we moved. Okay? And also it allows very easily add to the software. Okay? Any questions?
What is interesting, I have many previous students in Russia who are working in Intel, and they said me that Intel uses mainly C++.
Yeah. So you can see now when you talk about machine learning, people are using Python, for example. During my bachelor degree, Java was the top. But if you need to control what's going on, and this is on Intel vendor, C and C++, the best thing. Because other language like Python and Java, it's very abstract, and it will not allow you control the memory and what you register and things in the hardware itself. Yeah.
Since it's better to use C++, which is more of a low-level language.
Better than C. Okay, let's be very clear here.
I mean, in terms of higher low-level languages. So is it maybe better to use lower-level languages, like, for example, the assembly language, because it does not need any like compiler or something?
Yeah, of course. When you go lower, it's better. But you will go to very complicated way to do your... So we are doing HPC. You are doing a lot of things on the application. If you need to go to assembly, even to ones and zero to do the programming, go to this, but you will not be able to do what you want. So you don't need to go very close to the hardware to code it, or very far from the hardware. So you need to go to a specific level that you can control what you are doing. Okay?
Also, simply is hard to maintain, and hard to, it's not readable.
Of course, I don't know. Actually, I cannot count more than 2 or 3 people I know that they can code with assembly now. Okay, so everyone now is very abstract. Now with Python and machine learning, everything is more abstract. Okay. Okay, so I will talk about ExaGeoStat CPP. Okay, so we are still on the development stage, so we'll run some examples with Jan today. But the idea here that before we restructured the software to C++, we had 2 software, ExaGeoStat, and we did another software called ExaGeoStat R. Okay, R is a language. I don't know how many of you know about R. So R is a language, scripting language. We call it scripting language. So we did version of ExaGeoStat in R because most of the statisticians are using R as a language to do their work. Like when I tell you that, okay, you will do machine learning, you jump directly to Python. Because Python have the capabilities, have a lot of libraries related to machine learning. The same thing for statisticians. They are using R, and this is why we decided to actually have ExaGeoStat in R. Okay, to allow them to run things, because they have some problems with running C code or defining their environment variables and other things. And we had 2 software. The idea when we did the software is to do a rubber of the function that we have on C in R. Okay, and this wrapper thing was not the optimum thing to do at that time, but this is the capabilities I had myself at that time, is just to wrapper the C code. When we re-engineered the software to ExaGeoStat C++, actually now we have just one software. We call it ExaGeoStat CPP, but when you install it on your system, you can enable to use it under R environment. So now we have just one software which can run on the C++ perspective or an R perspective, okay? So in this environment or that environment. So today we will run some example in R as a statistician and see how much we can abstract the complexity of the hardware for the user. Because when you talk with statistician, I'm not talking about Mark and Jan here. They are expert, but in general, they don't know about GPU, hardware, tile size, the things that we discussed. We need to abstract everything to them so it's become easy to run ExaGeoStat on different environments. So this is the old ExaGeoStat R, just to give you the idea. We have just a wrapper over the layers, the stack, software stack layers that we have related to linear algebra, runtime system, if you remember the graph that I showed yesterday, and we just put a wrapper at the end. The problem of the wrapper compared to this design, who care about the software design, is the R has a separate memory space. C has another memory space. If you need to do a wrapper, this means that you need to move data from this memory space to that memory space every time you are running a single function. And this is impact the performance and the productivity too, okay? And this is why we moved to this new design, which we have one memory space and you can call it from R or from C. When we did ExaGeoStat R, we did a comparison. So to show the statistician, and this is something very important when you work on computer science or software, you need, if there is a competitors, you need to show yourself compared to those competitors. So at that time, there was two packages, R packages, Fields and GeoR, was most used, and I think until now, they are most used packages to do the MLE operation under the R environment. Okay, so we did one paper just to compare ExaGeoStat R with those two packages. It's not at all a fair comparison. Okay, because we are running parallel processing, we are running on GPU, supercomputers, and they just run on CPU. But we wanted to show the statistician the capabilities of our software compared to the most used packages in the market. Okay, so this is just a comparison about the functionality of the three packages, GeoR and Fields and ExaGeoStat R. So what's the function we are using, the function name here and there. Those parameters, we are talking about the matern kernel, for example, which has three parameters, the variance and the range and the smoothness. And some packages are estimating the three parameters, some packages like Fields, just two parameters. And what's the optimization method you used? So we know that we have a likelihood function that we need to run for many times to optimize a set of parameters related to the likelihood function. So those set of parameters, which on matern kernel, variance and range and smoothness, are running through the optimization algorithm. This optimization algorithm, you can use any optimization algorithm. Okay, this is another way to optimize your execution by running a very optimum optimization algorithm over the MLE. So to have a fair comparison, we just listed the optimization algorithm used on each package. This is, for example, this is three graphs to show the performance on one chip, 16-core Intel Sandy Bridge chip, Intel between changing. This is related actually to just ExaGeoStat. You remember yesterday that I said that we have to have a parallel processing for our matrix. I need to divide my matrix to small submatrices and give each processing unit one submatrix to work on. Can you remember this? So this is how we're parallelizing things. A big matrix divided to small submatrices, we call it tile, and then we distribute the tiles to the processing unit we have, CPU, GPU, distributed system. The main thing behind the performance is what's the tile size? What's the dimension of this small submatrix that you will take from the big matrix? Okay. Usually, we are trying to put one tile on the cache memory that can fit on the cache memory of our machine. Okay, you know about the memory hierarchical, right? Hard disk, RAM, cache, then the register and CPU. You know about this?
Yes.
So we have the hard disk, which is very slow and very cheap and very big. We have the memory, which is medium, medium, medium. We have the cache, which is very close to processing unit, but very expensive, and the size of the cache is very small. To have fast execution to any software, it's good that your data can fit on the cache. If it's on the cache, so it will fast move from the CPU and GPU. But if you go to the other level, of course, this cache will be small for your data. You need to put some data on the memory. So during the execution of your software, if the CPU cannot find the data on the cache, it will move it from the memory to the cache, then start work on it. So we have some overhead of data movement. Of course, if your data is very big and you use out of core and you are putting something on the hard disk, this will make things worse. So the idea behind the task-based parallelism or the tile-based parallelism we used, that we choose the tile size to fit on the cache memory of your machine. So when you move something from the memory to the cache, it should be a whole tile. It's there. The processor can work on the whole tile, do something, matrix multiplication, do Chomsky, any kind of linear algebra operation, then return it to the memory. This is the optimum case. This means that on different hardware architecture, we have different cache sizes. So you need to choose the tile size differently for each hardware architecture you are running on. So I have the same code running it on an Intel Haswell processor. Then I use tile size equal to 320, and it works very fast and good. Then I move the same code, and I try to use the same tile size with Intel Haswell processor, and it's slow. Why? Because of the cache size. So every time you are moving our software from hardware to another hardware, you need to tune this tile size. So this is a comparison to show the tile size with different matrix size. So N is the matrix size, and tile size is here. This is actually, we don't have the numbers here. But this is different tile sizes, and you can see here on the y-axis the execution time. On the x-axis is the number of cores. Okay? So I'm increasing the number of cores, and at the same time I have different tile size. You can see that some curves of those have bad performance, like the purple one. Okay? Because the choose tile size for this hardware was not that good. When you optimize it, you start to have better performance. This is some accuracy comparison between the three packages between ExaGeoStat R, Field, and GR to show that ExaGeoStat R can get the same accuracy as the other packages. So most important thing when you talk about scientific applications is not to talk about performance and the software capabilities, but also your accuracy, how far you are from the standards. Okay, if those software is the software that you use in the market and you need to compare with them, you should also show that you are getting the same accuracy as them. You can see here the beta and the variance, the smoothness and the range parameter with 100 samples. This is the average, and how we are very close from the estimation that we can get from the other packages. This is the speed up of ExaGeoStat R comparing to the fields and GR. So on the blue curve, it's GR, on the green, fields, and the red one is ExaGeoStat R. And you can see that we are faster than the two packages, not just faster, but also we can handle larger problem size on the same memory, on the same architecture compared to both. This is something else. We have a covariance matrix. We can do some calculation to know how much we can fit on the memory. So it's very clear. If I solve the problem, I will need 100 gigabytes of memory. If the other will solve the problem, he should use the same or need the same 100 gigabyte because it's the same problem. However, if your software design is not that good, for example, you are copying something extra here and there just to move the data. Sometimes we have variables that we are not using in the code. All of these stuff are taking more memory. So if your software is not designed very well, even we have the same problem size, you will not be able to reach or scale to larger matrix size on the same hardware, on the same memory size. And this is what you can see here. The other software actually stop on 20K or 22K problem size, but we can reach to 70K on the same memory. This means that the design of the hardware itself, regardless of the speed up, is better than the other softwares. The other softwares cannot run on GPU, for example. This is an example of running ExaGeoStat R on GPU and how we can scale with different number of GPUs and compare to the CPU one. So the CPU, for example, is the purple one. Just if you have GPU on your machine and you enable 1 GPU or 2 or 4, you start to see more or less execution time with the same problem size.
I have a question.
Go ahead.
How you have to fit the submatrix in the cache, and you have to make it dynamic for different machine. How you make it like this in the code?
No, again, I didn't get that.
You have to fit the submatrix in cache.
The tile, yeah, let's call it tile from now, okay? The tile and the cache.
And you have to make it for different machine, right? Different machine.
Different architectures, yeah.
Yeah. How you make it like this dynamically?
Yeah, this is a good question. So until now, the method that exists, I think just one method. So you are talking about this, to be clear. How to tune your tile size when you move from one architecture to another architecture. Currently, we are doing this manually, so we are choosing some until we are satisfying with this. Some people now are using machine learning for that. So learning from the running on different machine and decide on the future machine how it looks like. I don't like the idea so much, but this is the only idea that exists, okay? Some others are putting something called warm-up code on their code, like ExaGeoStat. When you install it, I can automatically, during the installation, try different tile size on this machine, then decide what's the best and give it to you. So just run 100 tile size with a small matrix size until I found what's the best and work on it. This is a research area, so I know how to do that, but I don't have time to do that, okay? So you need to understand what's your architecture, what's your memory size, memory bandwidth, cache size, register size, CPU, and you can do theoretically to know exactly what's the best tile size. So you can study this theoretically, not practically, and not using machine learning. Okay, but there is no exist way until now. Okay. Other questions? So these are some results with ExaGeoStat R again on Shaheen 2. Okay, and you can see that we can scale to 250K. And this is not a small amount, as we discussed yesterday at the beginning of lecture. Just try to compute the memory needs for a problem like that. And you will see it's terabytes, and you cannot do it on single machine. So we did this on distributed system, and this is show the execution time with different problem size and on different number of nodes on Shaheen 2. Okay, so this is also to show the capability of the software that's not exist on the other software. Okay, now we will go with Diane. She is a little bit sick. I am not sure if she can talk or not, but I will help her. So we will run some examples on one of the servers that we have here at KAUST to show you the performance of ExaGeoStat, to show you the meaning of changing the tile size, the meaning of changing the number of cores, and how to use the GPU, and how the function call, I'm talking until you can come in. So I'm wasting time until you can. So, and how fast we can run if we integrate the GPU, for example, on our code, okay? Yeah, okay. Nice to catch this. The what? Yeah, let's just... What's the problem?
No. This side is for the...
Oh, okay. I think I have one. I'm not sure. Do we have any more class here? No. Okay. Everything is good. Thank you.
It's hard.
Okay. So I will talk and Yan will run. She cannot talk. Sorry for that. Yeah, let's move this. Okay, let's move from the beginning. Excuse me. Okay, how many of you familiar with R? Okay, we have a good, okay. This is good. So who is familiar with R? R is somehow like Python, scripting language. You can run some statements and see the results and other things. So this is our package. ExaGeoStat CPP, you can call it on your code as R as a library. Yeah, let me do something here to easy to explain what's going on. Okay. So for example, if you look to line 3, we are calling our library. Then from line 4 to 9, we are defining some variables. This is very important variable for the performance. So N cores is the number of CPU cores that you intend to use. Okay. For example, the server we have here, we are running on, has a 40 core. Usually we are using N-1 cores on the software because we need one core just for the software and the other to run the example. So we are using 39 core. This is for you. It's up to you. I can see some people using the software and they are not aware of the hardware. Okay, 39 is very fast. Let's use 100 core. No, this is a software level. You need to align with the hardware. If you did 100 N core, this means that you will have double thread on each core, so you will not have performance. Actually, you will have problem of conflict between the cores. So you should use the number of cores -1 or less as you want. In line 5, this is the number of GPU if you want to use any GPU on your system. And DTS is the tile size on this example. This is the tile size which I told you to tune for each hardware architecture. We have something called LTS. This is a tile size but related to approximation method. We will not go with this example for now. Computation, how you need to do your MLE. So in ExaGeoStat now we have exact, we have low rank approximation, which I discussed theoretically yesterday. We have mixed precision, so you are defining which method you will use to compute your covariance matrix. Okay? Then you are calling on line 9 the hardware. So now I am setting the hardware, number of cores, number of GPU, and the computation. This is how I set the hardware. So from line 4 to 8, some variables. Then I give the main function hardware to define my hardware in line 9. Okay? Everything is good? So when you jump to line 13, this is my problem size. In the example that we will show today, as I said, we are still under the development of the software. So even today we will do data generation and modeling because the prediction is not there yet. But to show you how we abstract everything to the user just need to define the hardware he has. And he will not be involved in any kind of task assignment to the hardware or something. Just, okay, I have 5 cores, I have 5 GPU, I have 100 node on Shaheen, run. So he will not be involved in any assignment of the tasks on the low level. So problem size is the problem that we are trying to solve. To make things faster here, we are using 10K by 10K matrix. This is what we need to solve on our server. On line 15, we are doing the configuration of running our software. The configuration meaning the software parameters. So you can see here, N is the problem size on line 15. My problem size, what kind of kernel covariance function I will use? As I told you yesterday, ExaGeoStat now supporting more than 14 covariance function. And this is the science part. Okay, so here, for example, I will use univariate matter stationary. This is the covariance function I will use to generate my covariance matrix. Then the computation, which is exact, as I said. Tile size, you need to set one or both if you will run on low rank approximation. I theta, I will talk about this. We will do optimization, right? So I need to define lower bound and upper bound optimization. This is a simple optimization problem. What's my search space? So this is why we used LU and LUUP. This is optimization again. Do you need how many iteration until conversion? All you need to do, so we set it to 1000. Optimization tolerance. Okay, so when you do optimization, you need to set the tolerance to stop or to converge during the execution. And this is related to the prediction. Let's forget it for now. Any questions about what I said? We are still missing I theta. Any questions? All of you aware about the optimization idea? Guys, it's okay to ask. Sorry?
Optimization, I didn't understand what you mean.
The optimization?
Yeah.
Okay. So we said that we are solving on our problem a likelihood problem, which has the sigma covariance matrix. We need to solve this problem many times. Why? To optimize a set of parameters, the variance, range, and the smoothness. What's the meaning of optimization in a simple thing? You have one or more variables. You are looking on the search space to find the maximum or the minimum of a specific function when you set those parameters. When you set those parameters. For example, I have a function like z is equal to x plus y. I am telling you that I need to maximize this function. To maximize it, I need to find the largest or the best value of x and y, which makes z maximum. Okay? So what's x and y will be? This is the optimization I'm doing. I cannot do like that because to have z larger than or the maximum of z, it's infinity because I need x is very large and y very large. So on the optimization, we are putting some constraints. Okay, those constraints can control what's going on. So if I put the lower bound and the upper bound is 0 and 5, this means to maximize the equation, I need z to equal 10 because I will put x is equal to 5 and y is equal to 5 because this is the constraint related to lower bound and upper bound. This is what we are doing here. We have an optimization, a function. We need to maximize it by setting some parameters, which is the range, smoothness, and range, and variance. Once you maximize the function, those parameters are the parameters describing the spatial field that we have. We can take those parameters and use them for prediction. This is the main idea. Complicated? It seems complicated. Okay? So all of these parameters is related to the optimization itself. Tolerance meaning what on the optimization? This is the difference between two iterations of the optimization algorithm. When we reach to this point, this means that we reach to the convergence. Okay?
I have a question.
Okay.
Me as a, I should make a calculation to set these parameters.
You what? Sorry?
Me as a user,
Mm-hmm.
I should make a calculation to set this lower bound and upper bound.
Yeah, this is tricky a little bit. Okay? You can make them as lowest as possible for the lower bound and as high as possible to upper bound. But when you do big search space, it will take time to optimize the function. But we know about the features or probability of those parameters. That, for example, if you talk about the range mostly between 0 and 1. The range. 0 and 1. So usually you will find something in between if you didn't do anything to the distance. When you talk about the smoothness, yeah, you can go up to 2, for example, as an upper bound. Variance is a little bit not controlled. So usually when we run on a real data set, we are put very low value for lower bound, very high value for upper bound. This is one way to think about it. The other way, sometimes we are running the example, and when we found that one of the parameters stopped at the upper limit or the lower limit, this means that we didn't give much search space to the MLE. So we are repeating and we are increasing, for example, the maximum value. So if your range stopped at 5, and 5 is your upper bound, so you have a problem when you set the upper bound. So we run again and we increase the upper bound until we found that the estimated value is in between the lower bound and the upper bound.
So I have another question. There is a default value.
Did you understand the first question or not yet?
Yeah, I understand.
Okay, the second question.
Second question is I have to set all these variables. There is default value.
Yeah, there is default value if you didn't set. So I think the default value is what we are using here. This is the default value. Okay? If you don't want to set that, it's okay. It will use the default value. But we are putting everything here just for you to understand what's the parameter we need. Okay, I start to feel that we have a problem that some people not understand what we are doing. I thought that this will be the easiest part of the short course. But it seems that you have a lot of questions. Guys, ask. Please ask. We are here for that.
I understand that you are doing an optimization, but for what?
Yes. Now we want to first generate spatial data and then use the ExaGeoStat CDP to estimate. So given the data, we want to estimate the parameters.
Okay,
Yeah,
so you are here estimating the parameters. Okay.
Remember we talked the day before yesterday, we used likelihood to estimate the parameters in covariance function. So here we said the univariate means the data is univariate data. And here the Maton, we use Maton covariance function. So remember in Maton we have maybe 4 parameters. So one is the variance, one is the range parameter, and the smoothness parameter. And finally, we may have a nugget which represents noise when we generate the data. So here, our idea is to first generate the data and then estimate use the ExaGeoStat. We will compare the true and estimated parameters.
So this code estimates the parameters.
Yeah, using the likelihood method.
Let me go from the beginning. Okay? So assume this is the first minute on the short course, 3 days ago. So we have a function, this likelihood function, was depend on this covariance matrix. Okay? It's a function like z is equal to x plus y. This function includes 3 parameters. In the simplest case, the Maton kernel. Theta 1, theta 2, theta 3. I can put any values for these 3 parameters. And this will change what? The output, right? So we have here the y-axis is the likelihood value. On the x-axis, it's a combination of the 3 variables. So I will try, for example, 0.1, 0.1, 0.1. I will take them, fit on the likelihood value, and estimate what's the value of the function. So the value will be something here. I will do the same. This is the optimization. The optimizer doing what? It just changed the 3 parameters. Change. So at the end, you will have some kind of curve, right? With a lot of things. When you increase your lower bound and upper bound, you are increasing the length of this curve because the optimizer needs to try a lot. When you reduce it, it will be faster. Then at the end, this is the point where our likelihood function is the maximum. So what we are doing is just what we have here. We call them theta hat, which is the optimized vector of theta. This is what we are doing in ExaGeoStat, very simply. Now it's clear? Yeah, okay. Go ahead.
This code calculates the theta vector, right?
What's again?
This code calculates the theta.
No, this code is just insert different theta. Yeah, estimate the theta, not calculate it, estimated it. Because we are calculating the likelihood function, but estimating those.
Okay, I have a question. All this theta have to have the same value?
No, of course no. It's a combination. So when you have a lot of parameters, it's more complicated to the optimization algorithm because a lot of variations to do.
So the code will try.
Exactly. This is what we will see now.
Okay, that's fine.
It's okay now, guys? Do you have still questions? Now it's clear. Yeah, now I can say clear. Okay. So let's go back. So what I'm doing is just to setting the optimization values here. We missed I theta, you remember? Okay. Our code will generate synthetic data and try to model it. The idea, I will not go again to the science part, but the idea that this I theta is used to generate synthetic data. So I will assume that theta 1 is 1, theta 2 is 0.03, theta 3 is 1. Then I will generate the data. What's the job of the modeling function? Is to model the data and retrieve those value back. If we generate the data using those value, and we give the data to the modeling function should tell me that the parameter that fit the data that you give me is the same as what you used in I theta. It's what?
It will compare the estimate with.
Yes. So I used those. When I put those on the likelihood function, I generated the data. And I know that those three parameters is the only three parameters that can maximize the likelihood function. Now when I give my data to the modeling function, it should know that, okay, those are the three parameters that you used from the beginning. And this is why I said yesterday that we used this data generation for validating our code. Because if I just go and get a temperature data set, real data set, and I use my function to model it, and it gives me three parameters, how can I know that these three parameters are correct? This is some real data. So I am generating using synthetic data. I know exactly what I'm looking for, and I will see if the modeling can retrieve them back or not. But to be honest here, we are talking about Gaussian distribution, and the modeling will not fit exactly on those parameters. But being close to this parameter should be enough. This is the process. Okay? So on line, on line 18, I'm defining my problem because I will generate data if it's 2-dimension, 3-dimension. Okay, this is the dimension of the data. On line 20, this is to generate data. It's called simulate function. So I am telling ExaGeoStat, please simulate data based on the configuration I gave on line 15. Then on line 24, I use it for modeling. This is the modeling function. Okay? So Jan will run this here.
I didn't understand I theta.
Okay. What's the main objective? I think you like the board more than talking. What's the main objective? You have data. You are doing a modeling function to get what? To get theta 1, theta 2, theta 3, which is, as I said, theta hat, right? This is the main thing. The problem that when I develop my code, I don't know if I use the real data set, what's the results will be. So I don't know if I'm correct or not. So there is a scientific process is to what? Is to start with initial theta 1, which I called here I theta. Generate the data. In this case, when I model it, I am expecting that the modeling function will do I theta as estimated theta. This is what I am doing here. I put I theta for ExaGeoStat to generate the data, and I am looking for the modeling function to estimate theta equal or close to the initial one.
And the initial one, like these numbers came from what?
Just numbers I put, yeah. But actually it makes sense, so it means something. Okay, but we just put it. You can change it as you want. Okay?
Is the dimension of theta related to the that function is always 3, like, or is it related to the dimension of the sample?
The number of parameters.
Yeah.
Did you understand what I said?
Yeah.
Okay. The number of parameters here depend on the covariance function that you are using. If it's space-time, if it's univariate, multivariate, you need to, it has Gaussian property. So changing the covariance function will change the number of parameters. Yeah, you remember we used here univariate, matter, and stationary. This is a specific covariance function, which has 3 parameters. Jan will try today this function, and also, if we have noise, another function which has 4 parameters to also estimate the noise, for example. Okay? Okay?
I'm going back to the optimizer.
Okay.
Which optimization method do you use here? I'm asking about the optimization method do you use here?
It's linear optimization algorithm. Okay? So it's very simple optimization algorithm. So yeah. Okay? So there is nothing here complicated to non-convex, for example, optimization. It's convex, linear optimizer, just lower bound. We don't have constraints, just lower bound, upper bound, and the likelihood function.
Can we use like gradient descent or?
You can gradient descent or the other, but again, we didn't. We tried about 36 optimization algorithm. I tried 36 optimization algorithm, and I didn't find that making the optimizer complicated helps. And actually, this is a local optimizer. It's not a global optimizer, and it can estimate the parameter very well. Okay. So Peter Richlick didn't explain anything about optimization on his lecture. Yeah, so you should be expert after that. Okay. Any other questions? Okay. So yeah, can you run? So we will run now the script here. Yeah, go ahead. You need to be inside ExaGeoStat. Are you sure you can see?
Yeah. I put my Zoom on.
Yeah, you have your own glasses. Are you able to see? Okay. Yeah. Okay, let's go for the first iteration here. So you see, guys, this is our first iterations, for example. No, first one. Yeah, 1. So you see the model parameter. So the optimizer start to put numbers, starting from the lower bound, see what's the value of the look likelihood. It's good. Then on the second, it start to change the variance, for example, and see what's the likelihood. So the optimizer will go step by step until can find the maximum look likelihood value. Yeah. Can you just press enter? Yeah. So you see, many iterations we are doing. You are okay from the science part, the optimization, everything. Let's go back to the performance part. If you look to any iteration here, let me go to the other side. You can see here some timing for different operations. For different operation we are using. So the factorization time, DTRSM, matrix generation, forget about this. Did you remember the G flops per second that I explained yesterday? Can someone remind me?
I remember it's a floating superposition.
Yeah, it's the measure of the performance of our machine. So it's floating point operation per second. Okay? So this is showing the performance of our software in this hardware, which is about 1 terabyte. This is 1,000 G-flops, which is 1 terabyte, 1.2 terabyte. Let me tell you that the machine we are running on has theoretical peak of 1.8. So we can get with this problem 1.2 out of the 1.8. Okay, you can compute the percentage of the peak performance compared to the theoretical performance. Okay, so here we are showing the performance of our run. We need several iterations until we can get the estimated parameter, and again, Our target that the estimated parameter should be close to the I theta that we use to generate the data.
15,000 iteration?
Sorry?
Decide how many iterations it will be?
This is the maximum. Some people are saying that, okay, for me it's enough to have 100 iteration and I'm okay with the estimated parameter. Because again, it depends on you. Are you okay with what I optimized for you or not? But we put it 1,000 as an upper limit. It should stop before that. When it reaches to the tolerance of 1e minus 9. Okay, questions?
To machine learning algorithm works, like the epochs and the training.
Yeah, it's optimizer, yeah. Let me tell you a secret. So machine learning depends on statistics, actually, okay? So everything is statistic at the end, but they can show it better to the user, so they have...
The AI people took it from you.
Yeah, from that stat field. I'm not a statistician, but yeah, from the stat field. Everything is from there. Actually, MLE is used in different parts of machine learning for neural network and other things. MLE itself, but for sparse matrix. Okay, so we done. And the estimated parameter is 1.1, 0.03, 1.01. And this is the maximum log likelihood value that the optimizer can find. If we look to those parameters and the initial parameter, you can see it's close. Yeah, it's close. Okay, and this should be the case. Okay, everything clear? Let's go with the second example. Yeah.
It's like working like threshold, maybe?
The what?
The I theta.
Yeah.
It's like at the point that we want to stop at. Or
No. I theta is the value that we use to generate the data, not to stop at. But we expect, because we generated the data, it's not real data, we generated it, we expect that the estimated parameter should equal to I theta at the end. Not the initial guess. Yeah, it's the theta that we use to generate the data. Okay.
How come it stopped by itself? Does it have a threshold of how close it got?
The what?
How come it stopped by itself at 289 iterations?
Because of the tolerance we used.
Which is like the leniency?
The tolerance on the optimization, when you do optimization, the tolerance is when to tell the optimizer when to stop. And it means the difference in value between the last two iterations. So, for example, on 288, this is the log likelihood value. On 289, this is the log likelihood value. If the difference is less than 1e9, 10 to the power of minus 9, which we set here, the algorithm will stop. It converge. Okay? If it cannot reach to this restriction, it will go until the maximum iteration you put. Okay? This is the second one.
It happens that there is cases that it cannot solve.
Not cannot solve, but it's more challenging to solve. So, yeah, but this is another thing. So the parameter we used here, 0.03 and 1, something that easy to estimate somehow. For example, we have experience when you increase the smoothness, the last parameter is go to 2.3, for example, or something like that. It's very hard for the optimizer to get the values. But it's not impossible. If you go very far, because the problem that this curve, I draw it like that. But with some change on the parameter, the curve can look something like this. And it is very hard for the optimizer to get the maximum value because, as you see, it's very close, it's very smooth. Okay? And this is not a problem related to MLE or ExaGeoStat. This is related to the optimization in general. Okay? This is the second example. Remind me what's this example for? Yeah? This is for what?
The second one.
For what, sorry?
The second example.
Yeah, I know for what. I cannot remember.
3D.
Yeah, okay. So, yeah, we are solving the same problem in different dimension. So we said the temperature. Temperature meaning what? Temperature on the surface or on the sea. This is one layer. Sometimes you need to model variables in 3D. Like I need to model the temperature in sea, but on different layers of the sea. after 10 meter, 100 meter. So now we have this cubic problem. We have 3 dimension. ExaGeoStat can also solve this. So we are supporting 2D, 3D. We can support more, but because we are caring about climate weather application, this is what we are supporting now. So this example, I will generate data on 3D, as you can see here. Can you see that? 3D, I generate 3D data and try to estimate it. So it's the same idea. I don't think that we need to run this. Yeah. Let's go to the next example. Yeah. We are trying here another kernel. So the Mattern kernel, we know about it. It has 3 variables, variance, smoothness, range. But this kernel, for example, is Mattern kernel with nuggets. Do you know the nuggets?
That we eat?
Yeah, something like that. Yeah, when I joined this group 7 years ago, some terms like nuggets, I start to laugh like you. Exactly. What does that mean? Okay. So nuggets in statistics is noise. Okay, but they call it nuggets. Yeah, they have different terms than us. Okay. So usually the real data that we are dealing with maybe have some noise. And you need to capture the noise because you need the actual parameter of the data without noise. So this kernel, for example, has 3 parameters: smoothness, range, and variance, and another parameter, which is the noise. So this is just to show you. I need to generate the data using I theta, which is 1, 0.03, and 1, and I will generate it 0.2. So I will assume that we have 20% noise on the data. So I add this as a parameter. Then I will try to generate the data and estimate as usual. Okay, maybe you can run this, Jan. Okay, the same thing. We have the same performance. We have the same execution time per iteration. Again, remember that we are using 39 core, okay? And we are using the full capacity. So we are focusing now on the science part. Go ahead. Sorry? So represent noise. I mean, when you capture the data, yeah, you have sensors. For example, you are capturing data using sensors. There is some errors can happen because of those sensors for reading or during the transfer. You have, for example, some magnetic field around the part that you are capturing. So the noise, the source of noise is a lot. Okay. Even the data itself, once you have the data, maybe there is some change on the data or some missing values that you started to interpolate by yourself. So this is kind of noise. Okay. What's the time, Jan? Yeah, we have 15 minutes. Okay. So you can see now we have 4 parameters to optimize, the 3 and the noise. And you can actually see from the running that we are close to the parameters above. So the optimization algorithm actually can reach to a close number of parameters very fast. But to optimize it, you can't wait until the conversion. This is why some people think that, okay, fixing the number of iteration should help, because I don't want to optimize it to have a 6-digit after the decimal point. Okay, you can see now this is enough, for example, for me, 1, 0.3, 0.9, 0.2. I'm talking here. Or if you need to tune it to the end, you can just leave it running. Okay? Questions until we finish this?
In this example regarding the noise, are we cleaning the data or?
It's not cleaning. It's capturing the noise from the data, separated from the data, to be sure that the other 3 parameters are for the data itself. Okay? This is not the optimal way to capture the noise, but this is one way to do that.
Is it possible?
Okay, go ahead.
Is it possible that the noise is so big or that it takes a lot of the data sets or
or we should like recollect the data if the noise are running? And in which limit the data can't be processed or can't be implemented in this algorithm?
It's not just this algorithm. This is data science in general. If you have a poor data, somehow because of how you collect it, it will impact the output, your output. There is method to capture the noise, to remove the noise, to reduce the noise, but it will not work 100%. So this is also a research area, just a post or pre-processing for your data to remove the noise before doing any data analysis on it. This is a big problem.
If I have a real data set, can I use different kernel to estimate alpha?
This is a very good thing, very good question. We have a lot of kernels, but how we can use the kernels on the real data set? You should have some understanding of the feature of the data set to choose your kernel. So if you know that, you have the data set. If you know that your data is not Gaussian anymore, it's non-Gaussian, so now you need to capture the non-Gaussianality on the data set, so you need to use another kernel. If you know that your data is not stationary, it's non-stationary, so we have a kernel for that. So it depends on you as a scientist, data scientist, to choose the best kernel that you think it will fit your data set. Okay? So I am a computer scientist. Usually when I have a real data set, I go to Mark. What do you think, which kernel will work on this? So it's some kind of expertise on how to decide based on the data values, based on the image, based on a lot of things. So Jan told me yesterday, if we run the examples, we will have time until we finish. We will not talk, but it seems that we have a lot of questions. Okay, so done with the optimization, and you can see that now we need more iteration because we have more variables, and we can capture actually the initial one somehow with this example.
I think the noise affects the result. The previous result was better.
Yeah, this is a good point. Yes. Yes, even we capture it somehow, but still it impacts the results. Okay, let's go with the next example. Yeah, what about this? I will generate the data using nuggets. I will add noise, but I will model it assuming that there is no noise. Can I do that? Yeah, you can. Not very bad, but it will not be as better as having the noise. Okay, do you want to run this?
Yes, let's see the result.
Okay, let's run. Yeah. Mm-hmm.
The optimization here is equally for what we do manually by taking the log of the function and taking the derivative and equal to 0 to find the estimator.
No, again.
The optimization here is equally what we do for what we do to find what's the likelihood for an estimator manually.
Yeah, of course, but you cannot do it manually. Yeah. At the end, we are solving a mathematical problem, but using the computer. It's not by ourselves. Okay. Questions, guys? Questions?
So for the code that comes from noise, how does it process the noise? Does it remove it?
No, repeat again. I didn't hear you again.
For the code, when adding nuggets. So for example, when it's calculating data, does it account the noise or does it remove it and then calculate it? How does it process it?
No, it captures it. It's not removing it. Here, I am capturing the noise. There is some method that you can remove the noise from the data before doing the processing. But what I'm doing here, I'm doing the processing, and at the same time, I'm capturing the amount of the noise on the data.
I'm calculating the noise within my calculations and code.
Yes, but I'm not generating a new version of the data set without noise. No, just capturing it. And you can see here, guys, left side, you can see here that everything is optimum. I mean that we are running, we put the noise 0.2 and we capture it 0.2. We have this I theta, but this is because we have synthetic data, which everything there is clean and we generate it by ourselves. But when you go to the real data set, we saw a lot of problems. Okay, so when you go to the real data set, this is the problem. The estimation is not that good. Why? Because there is no noise, because there is stationary, there is non-Gaussianality, and we need to remove this. So the pre-processing step is very important when you are dealing with data science. Okay? Are you okay, Anne? Still okay? Of course, if you have methods to do a pre-processing on the data to clean it, this should be good. But the main problem, we are trying to do some work now with some institutes here in the kingdom with the real data set. A lot of problems. You have missing values. You have noise. You have some capturing in a wrong way. You have different sources of the data. So maybe you have sensors, you have satellite images, you have other things. All of these stuff have different degrees of noise, of instability, and you need to deal with all of this. So it's not that simple or just modeling everything is clean. No. Okay? And even in the field of spatial statistics, having new kernel that maybe captures some more parameters related to specific data is also a research thing. So yeah, we are adding the kernel to capture the noise, but there is other covariance functions that can help better to get this noise. Okay. So can you see the estimation now? So did you remember this example? We generated using nuggets, so we added nuggets, but we model without nuggets. And you see now the results compared to the first and second result we got, it's a little bit worse because there is no noise and we didn't capture it using our kernel. Jan, we have 8 minutes, so I need to run the other things. Are you fine with this? Maybe let's close it, Jan, and let's go to. We have 3 more examples, 5, 6, 7, 4 examples. Yeah, let's open the 5th one. Yeah, you remember the tile size? Now forget about science. We're done with science. Let's play with the hardware parameters. Okay, can you remember the tile size? We used on the first 4 examples 360 as a tile size, and this is the best we found on this machine. Now let's play with the tile size and see what? See the G-flops per second. You remember we reached to 1.2 terabytes, 1,200. So Jan, now we'll run this example where we put the tile size is equal to 760, not 360. Just changing the tile size and see how this will impact the performance. You see, even now, it takes time to do the iterations. No, it's better actually, right? We have 1.3 or 1.4. Yeah, 760 is better than 360. So now we have, here we post the performance a little bit from 1.2 to 1.4 just by changing the tile size. So as I said, you need to tune your tile size to get the best performance. 1.4 from 1.8 theoretical peak, it should be very close. So tuning the tile size should be very important. So even it's 1.5. Jan, please check to me if anyone ran on the server or not. So stop this. Are you okay with this, guys, to jump to the next example? No, we are okay. Yeah, let's go to the example 6. The number of cores. We are used the maximum number of cores on this machine. Can we reduce it to see what's the impact? So we have now 19 instead of 39. Can you see this on the third line? Can you run this example, yeah? We are using tile size 360, so what we are expecting is 1.2 terabyte performance. Let's see when we use less number of cores, what will happen. Of course, it should be like that. Can you see? It's 700. G-flops, not anymore 1,200, because you are not using all the cores on the machine. So you can play with this as you want and based on the hardware that you have, and it will impact the performance. And again, the performance impacting the time. So the total time here is 11 seconds. I remember there it was 5 seconds just to finish one iteration. So this will impact. I think it's enough, yeah? Let's go to the 7th example. Yeah. Can we increase the matrix size? So we are, from the beginning, we are using this 1,000 problem size. Can we run 2,000, 3,000, 4,000? Yes. Since it can fit on the memory of the machine, I think with this machine we reached up to 112K matrix size by 112K. Yes, and you can see the performance and also see the memory, the memory usage. We don't need to run this Yan2. Okay, this is just for different problem size. The last one, which is very important for me, is to use GPU. What if we use the GPU? We have 2 GPUs on this machine. We will use all the CPUs plus all the GPU on the machine to get the best capability with a very big matrix size, 50K, 50,000. Let's see that. Let's run this. Yeah. We put maximum number of iteration on this example to 5, just to stop faster. Okay. So any questions? This will take time because we have a big matrix size, but I will show you G flops per second. This is the important. We got 1.2, then we posted to 1.5 when we change the tile size. Let's see now. I added 2 GPU. What's the performance that I gain? Questions? Okay.
So for the optimization, when you have a couple different parts, you're generating a matrix and so on and so forth. Some of these take more time than others. So I remember with Peter on the first day, one of his methods sort of got around that by only doing that every so and so number of iterations. Have you tried something like that in one of your optimizations?
We didn't. Actually, this is the expertise of Peter Richrick. He is actually an expert on how to optimize the optimization algorithm to reach to the solution faster. This is something on our agenda, actually, maybe to collaborate with him to help us to reduce the number of iteration if he has something smart on this. Okay, so he focused on that because this is his expertise, to reduce the number of iterations. Okay? Did I answer your question or not?
Yeah.
Okay. Questions? Takes time because we have larger problem size now. Even we are using more resources from the system. This is the last example we will run. So after that, we're done. Yeah. Done at least with the data generation. Can you see the G-flops? It's 5,000. So we jumped by 5x just by enabling the GPU. Okay, and we can finish this problem on this time. Actually, it's very fast, but we have one problem on ExaGeoStat until now we are trying to solve, that we are generating the covariance matrix on the CPU, even we are enabling the GPU. And you can see here the most time-consuming part of the matrix generation because it's on the CPU. But the other one, the factorization, the other is very fast because it's run on the GPU. Okay? If we had time today, we didn't have time yesterday maybe to do one example, for example, on Shaheen to show you if we have multiple nodes or other things. But as I told you, everything is abstracted. You just need to set some number on the R code and you can run without understanding what's going on. But there is a lot of work that we did in the software itself to enable this. Okay? Any questions? We're done for today. You will not see us. Not again, but during this week, that's it. So if you have questions, let me know.
Can you use this ExaGeoStat online, the software? Can you use it online?
Online.
There is API?
Not online. You can download it and use it on your machine. We don't have, for example, a cloud service for ExaGeoStat. This is something else. But you can download it and install it.
It's on GitHub, right?
It's on GitHub, yeah. So we have this. Actually, those slides is on Mark web page. So you can go there, and there is a link for ExaGeoStat. ExaGeoStat are the old version, and ExaGeoStat CPP, how to install it. If you need to do, for example, a project in your last year or something related to ExaGeoStat with a specific data set, this will be very nice. Just let us know, and we will help. Okay.